limit comparison test, narrated by Dr. Rebecca Swanson, Colorado School of Mines. In this video, we are going to learn about a new test for series convergence or divergence called the limit comparison test. Additionally, we will discuss why this test works, at least at an intuitive level, and apply the test to an example. Okay, so the first part of the test says that if the limit as n goes to infinity of an over bn equals L, where L is non-zero and not infinity, then the series with the AK terms and BK terms either both converge or both diverge. If that limit is 0 and we know the B sub k series converges, then our series with A sub k terms also converges. If the limit is infinite and the B sub k series diverges, then our A sub k series also diverges. In all of these, you want to imagine the sum of the A sub k's being the original series you're trying to understand, whereas the B sub k series is going to be a comparison of your choice. And what we're actually comparing, however, is the ratio of terms in these series, the an over bn. So let's talk a little bit about why. Now, if we have the limit as n goes to infinity of an over b sub n giving us L, that implies that for large n, so think of n being greater than or equal to some large n, then a sub n over b sub n is approximately L. Or a sub n is approximately L times b sub n. If we look at our original series, the one that we're trying to figure out, we again have a partial sum at the beginning. That's just some number that we can calculate. And then we can replace each of these terms, as long as I make an approximately symbol, by multiples of the b sub n terms. Or in other words, we're saying that our original series is approximately s sub n minus 1, some number, plus L times a series summing from k equals n to infinity of b sub k. And this is where the first item comes from. If we know that our b sub k series converges, we can chop off some of the beginning terms, it's still going to converge. Then we're just adding other stuff to it or multiplying by a constant. Our original series will have to converge. Or if we know that this b sub k series diverges, then our original series will have to diverge. Again, as long as L is neither 0 nor infinity. And in these cases, again, that approximately symbol is important. Now in the cases L equals 0, case 2, then our terms are approximately 0 in ratio. And this is more of a kind of hand-wavy but intuitive argument. But in this scenario, we also needed that the b sub k series converged. For a series to converge, its terms must limit to 0, so we know that the b sub k's limit to 0. And the only way for this to happen is if the a sub k's go to 0 even faster. And so we can only make a conclusion here if we have that information about the b sub k's going to 0. We'll also get that the a sub k series converges. In the third L equals infinity case, then again, our a sub n terms, even if they was required, they would have to be approaching 0 slower than the b sub k terms. And we can only then make a conclusion if b sub k series diverges and conclude that in that case the a sub k series diverges. Again, these two are a little bit hand-wavy. This is the real idea you want to think about as long as L is not 0 and not infinity. So let's actually apply our results. So let's try and utilize our limit comparison test. Again, our original series is the a sub k series, so a sub n better be equal to the corresponding terms. Now, if we go back to this test for a second, I told you over here that we're going to compare to something that we have to choose. What we compare to is not dictated to us by this test. I have to make a choice. I want to make a good choice. So what I want to do is kind of focus on what a sub n looks like. Now I see polynomial term n plus 2 over another polynomial term n squared plus 3. So to me, in the numerator, the highest degree term is n, In the denominator, the highest degree term is n squared. So a good choice for me might be to set my b sub n's to be 1 over n. Because I can kind of think of in the long run, for large n, the 2 and the 3 aren't going to matter much. All that's going to really matter are the n and the n squared terms for large n behavior. Now, back one more time. I do have to note that my terms are positive for the series to work, at least from some point on. So mostly you just have to state that, let me know you've thought about it. Now we have to consider the limit an over bn. So I've substituted my an and my bn terms. I'm going to multiply by the reciprocal instead of dividing two fractions. Multiply this through and simplify. This is a good scenario where I might want to multiply by 1. I know that this term's going to 0, and that term's going to 0. So my limit is 1. Since L equals 1, we know L is not 0 and not infinity, so we are in our first scenario. One more thing we have to figure out, though. Okay, let's go back to our test one more time. All we know is that these series either both converge or diverge. So we still have to actually analyze our comparison series. So we did the step where we checked they're positive. We have a limit. Now we have to say what happens to our b sub n series. Well, this is a series that we've seen and we know. This is the harmonic series, so it diverges. Of course, you could have also applied the p-series test. And now we are ready to make a conclusion. Our original series must also diverge. So to close at this point, you should recognize the limit comparison test as another series convergence or divergence technique and be able to apply it in simple cases. You'll get more practice in class.